Get ready to join us on our latest journey. The Compass is the podcast that travels far and dives deep to help us find our way in a complex world. Welcome on board. Podcasts from the BBC World Service are supported by advertising.
At any moment, the predictions of your local weather forecaster might be suddenly superseded by space weather, a special breed of storms fomented on the sun and launched toward Earth with potentially devastating consequences. Most of the time, the solar wind billowing out from the sun blows right past our planet without causing any ill effects whatsoever. But an unexpected eruption on the sun's surface might spike that wind with enough charged particles to make us wish we'd known what was coming.
Space weather's always been around ever since the Earth and the Sun formed 5 billion years ago. What has changed is we have technologies that are vulnerable to space weather, and those technologies like the power grid, like satellite navigation, are very important to the way we live today.
There was one in 1989 when the whole of Quebec was in darkness. Elevators stopped. People were trapped in lifts until they got rescued, and that lasted for 12 hours.
While an ordinary blizzard or hurricane destroys buildings or drops enough rain to turn rivers into floodwaters, a downdraft of space weather could disrupt power grids all over the planet, knocking out navigation systems and communications networks. The threat is so real and the concern so global that countries around the world are working toward better means of reading the sun.
మొదట ఆదిత్య 1 పేరుతో విజిబుల్ ఎమిషన్ లైన్ కరోనోగ్రాఫ్ అనే ఒక పరికరం ప్రయోగించాలని భావించింది. ఈ 400 కిలోమీటర్ల
The sun, our star, the source and sustainer of all life on Earth, the only object in the solar system that shines. The sun's light defines what we mean by day and night. The turning of the Earth that wheels us in and out of the sun every 24 hours seeps into every fiber of our being. I'm Davis Sobel, orbiting the sun, thriving on its energy, basking in its heat, marveling at its power, reveling in its light. And today, trying to predict storms from the sun, our star, here on the BBC World Service. Aditya, the Sanskrit word for the sun, is the name of a new satellite now being readied near Bangalore, India, to monitor the sun for weather signs.
We are having this complete jumbo suit, what we call. It covers
Visitors to this satellite laboratory in Karnataka need to cover up in special suits, gloves, and surgical face masks, and also pass through a shower blast of contaminant-free air before entering the pristine facility.
So that eyelashes should not come out and it should not contaminate critical elements.
Here, scientists from India's Institute of Astrophysics are preparing Aditya, the country's first solar mission. Each of the 7 instruments or payloads aboard the spacecraft will observe a different aspect of the sun. Raghavendra Prasad, the chief investigator, describes the various payloads.
Aditya mission has a suite of 7 payloads. Okay, 2 primary payloads are study the solar corona. The second payload is what's called SUIT, Solar Ultraviolet Imaging Telescope, that studies the photosphere of the sun. Then we have 5 more payloads, 2 of them for imaging of sun in the X-ray domain, and the next 3 payloads are the particle analyzers, which will measure the charged particles that are coming in from the sun. There's one more instrument which is called the magnetometer, which will study the solar magnetic fields actually.
Essentially, coronagraph is an instrument which mimics a total solar eclipse kind of scenario.
Professor Dipankar Banerjee is responsible for assembling the spacecraft's principal observing instrument, the coronagraph.
The first thing what we need to know is if there is a big explosion is happening in the sun, and if that such explosion happens, we call it a coronal mass ejection. A huge amount of mass is being dumped into the corona, and that amount of mass travels towards Earth. So coronagraph is the ideal instrument to capture that movement of that big blob of plasma which can travel towards us. And coronagraph will allow us to calculate its speed at which it is traveling, how big that plasma blob is, what are the constituents of this plasma blob. If the plasma blob has a lot of highly energetic electrons and protons, they are more harmful for us. So we will have a capability of predicting when it can arrive and what kind of effect it can cause when it reaches Earth.
Fortunately for us, the Earth's magnetic field cocoons the planet inside a protective bubble. Catherine Burnett is Space Weather Programme Manager in the UK's Met Office.
People imagine the Earth's magnetic field like a bar magnet. So you get nice rings of magnetic field coming from one pole and going round and joining to the opposite pole. The solar wind pushes on the Earth's magnetic field, so it's not quite that nice, even pattern on either side. The solar wind pushes it flat on the side of the Earth that faces the sun, and then as it rushes past the Earth, it drags that magnetic field out into what's called the magnetotail as it moves away on the night side of the Earth.
Dr. Nikki Fox, Director of Heliophysics at NASA.
The magnetic field, this magnetosphere, is what really protects us. So if you think about like a rock in a fast-moving stream, the water is coming down, you get that bow wave at the front of the rock, and then you get the turbulent flow that comes out behind. And that's what our planet looks like with its magnetic atmosphere as it's traveling around on its orbit.
Aditya's destination is a stable point between the Earth and the Sun known as L1. It's one of 5 such locations in space named for the 18th century astronomer who described them all, Joseph Louis Lagrange.
For anyone who doesn't know what the Lagrange points are, they're effectively points in space where the gravitational pull of the Sun and the gravitational pull of the Earth in this instance are balanced. So they are good points for basing spacecraft without needing to use a lot of fuel to keep them in position. A lot of the spacecraft that give us images and data from the Sun at the moment are at the Lagrange 1 point, which is in direct line between the Earth and the Sun.
Aditya will join other satellites already stationed at L1, including SOHO, the Solar and Heliospheric Observatory, a joint project of the European and American space agencies that is still operating optimally after more than 20 years of keeping an eye on the Sun. That job is just too big for any one mission. Most of the others are not confined to Lagrange points. Stereo, which is a pair of twin spacecraft launched in 2006, provides 3D images of the Sun from 2 viewpoints. The newest satellite on assignment to the Sun, NASA's Parker Solar Probe, launched from Cape Canaveral in Florida just last August, also seeks to understand the corona.
Parker Solar Probe is primarily targeted towards the study of the solar wind because it is traveling through the solar wind at different times, at different locations and so on. And the other interesting thing is it's going to go very close to the Sun. So it will allow us to study the properties of the solar wind in situ, very close to the Sun. So Parker Solar Probe is not going to look directly at the Sun, whereas we are going to look primarily towards the Sun. So the combination of the data from Parker Solar Probe and our mission will be very useful, particularly for the solar wind studies.
And for the all-important prediction of space weather.
Space weather affects everybody. It affects the whole planet. The key thing for space weather is having sentinels in all of the really key locations. And so you want some that are looking at the Sun and telling us what the Sun is doing. Is there a particular area on the sun that looks like it could suddenly get very active and have a big solar storm, where is that in relation to the path of the solar wind and the Earth? Are we looking down the barrel of a gun at that point and waiting for the big explosion to happen and then we know it's going to impact us? Is it going off the side, in which case we're not in that direct line of fire? We want to also have spacecraft that are sitting out in front of the Earth and telling us really what is about to impact the Earth, so we can do very precise last-minute forecasts of, hey, it's really here and this is what we're really seeing.
Glimmers of space weather appear to us primarily near the North and South poles, where charged particles emanating from the sun draw harmless, gorgeous curtains of colored light across the sky. Mike Hapgood is head of the Space Environment Group at Rutherford Appleton Laboratory.
The aurora is probably the most spectacular part of space weather that we can see with our own eyes. The Vikings had a lovely idea of aurora. They compared it to a woman dancing. And when you see a really spectacular aurora, it's like that. These slowly moving patterns of light are like the tail of a dress spreading around when somebody's dancing. And so a princess in the sky dancing is one of the old myths that they had with that.
It's thought to be there for many thousands of years, that there are historical records of strange things happening at lower latitudes.
Dr. Mario Bisi also works with the Space Environment Group.
Back then they had no clue, but today we can say, well, maybe it was a strong storm, maybe it was aurora, maybe aurora did reach as far as parts of southern China and India and things where there's some reports. I mean, it has been reported that in semi-modern times, the aurora was seen over the Caribbean, for example. So it isn't unknown, but it's one of those rare things that may be considered a 1 in 100 or 200-year event.
Those ancient observers had no premonition of the spectacle, and no space-age equipment that could be damaged by it. Dipankar Banerjee.
One thing one should note that the space weather effect to countries like India is normally much less effective. But now we are going into the space more often, right? So we have several satellites. So space weather effects can damage our satellites more often. So that is one area which we need to worry about. Also, we need to worry about our long-haul flights. And most of these flights go through the polar region. And the passengers in those long-haul flights can get affected by the additional radiations which comes because of these large flares and coronal mass ejections.
Dr. Alex Young is the Associate Director for Science in the Heliophysics Science Division at NASA's Goddard Space Flight Center.
All of this phenomena is basically electromagnetic. And so in that sense, it is interacting with our technology, which is electromagnetic. The light and the particles that are flowing into the upper atmosphere change the properties of the atmosphere. So the outer atmosphere is called the ionosphere. Not a typical gas, but an electrified gas, an ionized gas. But when all of this space weather impacts that part of the atmosphere, it changes it. And so certain signals no longer travel around the Earth, or they no longer travel through the atmosphere. There are lots of aspects of society that are dependent on that. And when this giant blob of solar material and magnetic field interacts with the Earth's magnetic field, that generates electrical currents in the upper atmosphere. And typically those currents actually flow into the ground. They're ground currents. But the problem is when current flows, it flows through the path of least resistance. And one of those paths can be large conductors that we have put across the Earth. Those, for example, would be long transmission lines for power systems or even pipelines. And so when the currents are strong enough and they end up directing themselves through transmission lines, that current can overwhelm power grids.
Such incidents are rare, but a particularly famous one is featured in the exhibition about the sun currently at London Science Museum. Curator Dr. Harry Cliff showed me this important early account of space weather.
This is Richard Carrington's notebook. So Carrington was an astronomer working in the middle of the 19th century, and he had his daily ritual, which was, if it was a clear day, his private observatory, which he built himself. He would go to a telescope, he'd project an image of the sun onto a piece of card, and he would sketch what he saw. So this particular day, there was a really big sunspot on the surface of the sun. He'd just finished drawing it when suddenly this bright, searing light appeared above the sunspot. And Carrington was really shocked by this. He thought maybe some light had penetrated the screen that he was using, and he realized that wasn't happening, that it was actually something happening on the sun that no one had ever seen before. And this is what we now know as a solar flare. So it's essentially an incredibly bright flash of light going from visible all the way up to X-rays and very high energy radiation. So Carrington sees this flare, he excitedly notes this down in his notebook, and you can see his original notes here. He sits around for a couple of hours waiting to see if the same thing happens again. It doesn't. But then about 18 hours later, the most incredible auroral displays bathe almost the entire planet in light. The sky goes a kind of incredible variety of colours from red to green to violet. People don't understand what's going on. It's almost like some people think the end of the world's coming. And at the same moment, telegraph system, the main means of communication in North America and Europe particularly, ceases to function. People have real problems sending messages. There's this big geomagnetic storm, essentially, that bathes the entire planet. And this is the first moment that scientists realize there's possibly a connection between something that Carrington sees on the surface of the sun, this flash of light, with aurora and with geomagnetic phenomena on the Earth. And it's the beginning of our understanding of what we now call space weather.
So interestingly, the same event, the Carrington event that has been well documented, actually had very strong signatures for geomagnetic storms, even in India.
Dibyendu Nandi, the head of space sciences at the Indian Institutes of Science, Education and Research.
We had the observatory, which in fact still is maintained by the Indian Institute of Geomagnetism. So this Colaba Observatory near Bombay, in fact, recorded the Carrington event. So the impact of this was felt even at very low latitudes and in India.
Maria is the first Category 4 to hit there in nearly a century. 150-mile-an-hour winds ripping buildings apart, knocking out power everywhere.
Imagine what happens when space weather intensifies at the same time as a storm in the atmosphere.
Massive flooding to come.
Mike Hapgood has a pretty clear picture.
You could have lots of big problems happening at the same time, and that would be very chaotic. A good example of that actually happened a year ago in the Americas with the hurricane season of Hurricane Maria that hit Puerto Rico. At the same time as they had all those hurricanes happening, we had bad space weather, and that really was disrupting the emergency communications links that were being used to coordinate the rescue efforts, the recovery efforts after the hurricanes. And it has been very much highlighted as a good example of two natural hazards occurring at the same time can make life so much more difficult than just one alone.
What is actually happening on or in the sun to produce these effects? Leon Golub is a solar expert at the Harvard-Smithsonian Center for Astrophysics.
What's powering the sun is the nuclear fusion that's going on in the core. And the weight of all the material above the core compresses the inside of the sun so it gets very hot, very dense, to the point that you can start nuclear fusion going. So that energy down in the middle of the sun has to escape. And as it radiates out, it becomes diluted and the temperature drops. So in the middle, it's about 15 million degrees, and it gets cooler and cooler as it comes out. But at a certain distance outward, something different happens. When the temperature drops far enough, the radiation isn't the most efficient method of transporting energy anymore. It becomes convection, and you get material flowing upward. The material actually carries the heat. Now that turns out to be crucial for generating magnetic fields. Inside the sun, about 1/3 of the way in, there's a boundary between this radiative transport and the convective transport. And right there, there's a layer where the magnetic field is generated. 10,000 times as strong as the Earth's field. What happens to that magnetic field is it becomes unstable and pieces of it float upward and reach the surface. And where they break through, you see sunspots. That's the most visible manifestation. But there's a whole volume of magnetic field that has broken through above the sunspots. And that's where the activity is produced. And all of that feeds energy up into the corona, which is stored until it reaches the point that it can't hold it anymore, and it becomes unstable and it erupts. And that's what we see as a coronal mass ejection, that eruption of the magnetic field and the coronal material all together leaving the sun.
Visible solar activity has fascinated scientists for centuries. You find accounts from China, from Mesopotamia, from Mexico, and more recently, the 17th century sunspot drawings of Galileo, which he made by letting the sun's image fall through the telescope tube onto a piece of paper where he traced the designs. But it was the brilliant solar astronomer George Ellery Hale who intuited the significance of sunspots and what they reveal of the sun's electromagnetic energy. Tom Kurz is an astronomer at the Royal Observatory, Greenwich, in London.
Hale was curious about the physical mechanism behind sunspots. And because Hale knew that different regions of the sun rotated at different rates, he was also able to understand that the sun's magnetic field would become very tangled up. Hale knew that where the sunspots were occurring, magnetic energy was causing a local cooling in the sun's atmosphere, and there was a lack of hot material there, which made those regions appear dark. And he went on a little further to understand that the regions actually appear on a cycle lasting around 22 years of total activity, and we actually often refer to this as the Hale cycle today.
Hale's unique invention from the 1890s remains a crucial tool for the analysis of activity on the sun.
What we can do with the spectroheliogram is see where the active regions are. They produce brightness in the spectroheliogram, which is associated with the existence of this strong magnetic field. And you can tell that there are active regions on the sun. You can, to some extent, tell that they are becoming likely to erupt. So it's a statistical forecast that it allows you to make. And the forecasters do that, looking at spectroheliograms in the light of hydrogen, H-alpha it's called. They can make predictions every day.
3, 2, 1, 0.
I rarely hear of space missions other than those launched by NASA. But in fact, India has a strong presence in space. Just last September, the Satish Dhawan Space Center in Andhra Pradesh sent up the 27th of India's satellites, and another 25 are now in development, including Aditya L1, which is drawing astronomers back to India to work. Dibyendu Nandi.
Initially, when the mission was planned, it was only envisaged to be a small satellite just looking at the propagation of CMEs, the solar storms. Then subsequently what happened was when this mission was being planned, a lot of young scientists, well-trained from various countries like US and UK, Belgium, various parts of the world came back to India, and I'm one of them, and we brought in expertise which was much more diverse. And we got into a discussion with ISRO, and we realized that pulling in this expertise, we could in fact have a much more comprehensive, great solar observatory, if you will, which can look at all domains of solar activity, right from the genesis of solar storms, how do they originate close to the sun, to how they propagate out of the sun's corona into the interplanetary space. So then we this mission proposal sort of evolved, and ISRO was willing to look at making it a much more comprehensive solar observatory.
Another kind of expertise resides in us. The average human is supremely well equipped to analyze the complex patterns on images of the sun so as to predict space weather.
Hi, do you want to come in? Shall we go through to the observatory, which is really a shed?
Julia Wilkinson is a citizen scientist who helped organize the Solar Storm Watch project for Zooniverse.
Solar Storm Watch enables anyone to help scientists monitor solar storms. There are about 16,000 of us Solar Storm Watch volunteers. We come from all over the world, literally. We have volunteers in the States, in Canada, Great Britain, all over Europe, India, Australia. We look at images from the stereo spacecraft. These are scientific images because we're doing real scientific work. Because we're given not one image to mark at a time, but 3 consecutive ones, then we can see how the storm is moving out from the sun towards the Earth. One of the reasons that I think Solar Storm Watch has been successful is that it's not the kind of project that you can use computer algorithms to, or you can train computer algorithms to look at the images and make sense of. Human eyes are very good at spotting the very faint and tenuous solar wind that these images portray, and very good at drawing around sometimes quite complex shapes that these storms have, whereas computers can't do that yet. Anyone can join in. You don't need to be an expert in astronomy, you don't need to be an expert in science, you don't need to have had any other training than that which is offered by the project itself. There's a little tutorial you go through. So anyone who heads down to solarstormwatch.com would be more than welcome to join in. Help save the Earth.
Next week, I'll be hiding away in light deprivation, uncertain whether it's day or night. I'm Davis Sobel. The Sun, Our Star is a cast iron radio production for the BBC World Service.